Let's try that again.
That's
All right, class. Thank you. We are now beginning right as soon as the bell has rung.
Ding.
Okay. I see that all of you already have all of your notes out, and everything is already set up, which makes me extremely happy.
What are you trying to do?
Let's talk about this. Which of these objects is in equilibrium?
All of them.
B.
Let me read the sections here, all right? A car driving down the road at a constant speed, a block sitting at rest, a skydiver falling at a constant speed, or all of the above. Which one is in equilibrium?
B.
All of them.
B is the correct answer.
I said B.
B sounds a lot like all of them,
Yes.
doesn't it?
B is a correct answer.
It's all of them.
So it's A.
A is also a correct answer.
C.
Okay, all right. Wait a second. Hold on. I'm confused. I'm a student who says equilibrium means it's not moving.
No, equilibrium means there's no acceleration.
Okay. No acceleration? Yes. Maybe another way we could put that is we would say there is no net force, which implies no acceleration. Now, if there's no acceleration, that means that velocity is constant. It could be constantly moving, so it could be constantly zero or it could be constantly anything. But if it's constant, I right now am in equilibrium because I'm moving at the same pace. Yeah, dynamic equilibrium. Because I'm moving, but I'm in equilibrium. No net forces. So yes, all of the above. Very good. All right, let's do some statics problems, shall we? This college level work here. An orange utan weighs 500 newtons hanging from a vertical rope. What is the tension in the rope? What in the world? Is you put it away, thanks. So here we go. There's the orangutan. All right. We have already circled him. How great is that? They've already identified the tension and the weight. So let's go ahead and draw a free body diagram. I'm going to draw a weight going down. Shall I make tension shorter, longer, or equal to?
Equal.
Equal. By the way, you have this problem in your notes, correct?
Yeah.
Okay, so if you don't have those out, why am I going to write it equal to?
It's
not moving.
It's not moving. If it was longer or shorter, then that would be the accelerated. So, all right. Now this one is like super easy. I mean, weight is 500 newtons. What must be the tension? It must be 500 newtons. You know that. I know that. But in our future problems, we're going to have so many different things going on that we're not necessarily going to know that. So I'll show you the equation that we would write. It's our old friend, Newton's second law. Summation of forces in the y direction is equal to mass times acceleration in the y direction. So everything that's going up is positive. So I'm going to put T. Everything that's down is negative. Minus W equals mass times acceleration in the y direction. Now this is the thing I'm going to do over and over again. I will always then ask you, is there acceleration in the y direction? And sometimes it'll be yes, sometimes it'll be no. In this case, it happens to be no. So I'm going to do this little trick here, right here. I'll say that goes to 0. Because acceleration is 0. 0 times, who cares what his mass is? It's always 0. So we have tension minus weight equals 0. If I'm solving for tension, I'm going to put weight on the other side. So tension equals weight. Once I have the quantity which I'm looking for isolated on one side, then I can do all my substitutions. In this case, my substitution is just one value, so it goes super fast. It's just 500 newtons. But I want you to see the long way for an answer that you already could pretty much see, because in a minute we're going to do some of the long ways and you won't immediately see the answer. Okay? But this is everything. The picture, free body diagram, Newton's second law, getting an answer. Now you know why we did this so many times and we've done this. Now it just seems like a snap, right? First couple times I taught physics, I didn't do any of that stuff. And we got to this problem like, well, let's talk about the forces and let's draw the free body diagram. And by the time we're even over here, everybody's checked out. But at this point, y'all are like, all right, let's get something a little more interesting. like this one right here. A car with a mass of 1,500 kilograms is being towed at a steady speed by a rope held at a 20-degree angle from the horizontal. A frictional force of 320 newtons opposes the car motion. What is the tension on the rope? Now, does anybody know what the tension on the rope is on this one? Just off the top of their head, 500 newtons? Yeah, not so much, okay? So we need to start talking about all the forces. It's nice they've got a picture here for us. Do you have that picture there on your paper? Great. So they say there's normal force, there's weight, there's tension, there's friction. I'm going to give you about 1 minute, that's all it should take. Draw the free body diagram of that object right there, of the car. All right, see lots of good stuff going on there. Let's see here. We've got the weight. And we want to make this kind of accurate. Did y'all make the normal shorter, longer, or same as the? About the same? Okay. I'm not going to hold you to that, because actually it's not. But tension over this way. And I may put it 20 degrees right there. Friction, which way is friction going on this? What's it again? To the left. I'll make it kind of shorter there. Great. Anybody bothered by this tension? Yeah, we're going to call that TX and TY, Tex and tie. Alright. We've got all this stuff, but let's just be honest here. We could do all sorts of analysis, but we want to save ourselves some time. What are they even asking us for?
The tension.
Find the tension, okay? Anybody have any ideas on what we should do next? Say it again? The X and Y, okay. So, well, I don't know what the number is right there. But I could say Tx is equal to, yeah, T cosine 20 degrees. That's about as best as I can get here for Ty, for tie, T sine of 20 degrees. Okay. Let's go through here and write some other information down. This is a car with a mass 1,500 kilograms being towed at a steady speed by a force held 20-degree angle, a friction force of 320 newtons. Okay, we need, yeah, probably Newton's second law. We've got two options for Newton's second law. We could write the one for the y direction and one for the x. Might as well just put both of them and see which one is more helpful. So, summation of forces in the x direction is everything that's positive to the right. So, t cosine 20 degrees minus f equals mass times acceleration in the x direction. Summation of forces in the y direction, t sine 20, because it's going up, plus n minus w equals mass times acceleration in the y direction. Okay, now I heard somebody saying something over here after I wrote this one down. I do have the mass. What is do we have the acceleration? Steady speed means at it's like at 2 miles an hour. That's what steady means. It means it's not changing. Okay? So if it's going at a steady 2 miles an hour, what is 0? Then acceleration is 0. Okay? So steady speed means, steady means constant. Speed is the absolute value of velocity. So constant velocity. So acceleration is 0. Hey, that's pretty good. Doesn't that mean that t goes? Yes, it does. If you think about this, do I know f? Yeah, I know what cosine 20 is. I can just set it to the calculator. So, and I know that this is 0. So actually, this right here is enough information for me to figure out what t is. I can figure out over here, but why even bother? Actually, I don't know what the weight is. I know what the mass is, but the mass is not the weight. You're gonna have to wait till Monday to figure out what the relationship is between mass and weight. Don't read ahead. Okay? So we want to figure out what t is. So t cosine 20 degrees minus f equals 0. Remember, we always want to solve for the variable. So I'm going to put f on the other side. T cosine 20 degrees equals f. So t equals f divided by cosine 20 degrees. That is about to get thrown away. I've got everything solved for t, so I can just substitute in. Friction force value is 320 newtons. Cosine of 20 is just cosine 20. Make sure your calculator is in degree mode.
340.5.
Say it again.
I got 340.5 back there. That's right. Ooh. 340.5.
340.5. I have 340.5. This motion has been made and seconded. All those in favor say aye.
Aye.
All those opposed say nay.
Nay.
Can you be for and against something?
Very
Neutral.
easily.
Neutral.
I guess if you have a postmodern mind.
Everybody.
Basically.
So, all right. Does that seem realistic? 340 newtons? Or 340.5 newtons? I mean, that's a lot of, that's several hundred newtons. Is that realistic?
Yes.
Why?
Newtons aren't like huge. They're
Because a car is heavy. Okay, and so what are you saying?
not. I mean, newtons aren't that huge.
They're not that huge, okay. I'm gonna look at it, also gonna, what you are saying is helpful if you know how much a newton is.
It goes into a pound 4 times.
Goes into a pound 4 times, so there's 4 newtons in a pound, is that what it was?
Yeah, I think
Yeah,
it
I think
was.
so.
Okay.
I was paying attention.
Very good. Yeah, another thing that you can do is, okay, so this is 320, there's 320 friction force. So this tension better be at least 320, okay? If it has to be 320 if it was just going to the right, but it's going a little bit up as well. So when you start pulling up on something, okay, then obviously some of it is being horizontal, some of it is being pulled up, but you're gonna lose some of that, okay? If you're pulling up at 340, then only some of it is going to the right. In fact, it's 320 is going to the right. Okay, let's see if we are correct. Wow, they did a whole lot of stuff, but look what their final answer was. 340. Exactly the same as us. They did their whole significant figure thing. Hey, Susie, with us? Thanks. All right. They have a nice little assess paragraph here. Sometimes helpful to look at that. Had we pulled the car with a horizontal rope, the tension would need to exactly balance the frictional force of 320. Because we are pulling at an angle, however, part of the tension in the rope pulls up on the car instead of in the forward direction. Thus, we need a little more tension in the rope when it's at an angle. So our result seems reasonable. Yeah, and by the way, that little bit of it that pulls up, I guess it's not showing there. There's a little bit that pulls up, that actually makes the normal force a little bit less. We'll talk about that another day. All right, here is a ring pulled from 3 forces. The ring is not moving. How How big is force F? Well, I know that. It's got 10 newtons that way, 10 newtons that way. It's got to be 20 newtons that way.
No.
Mm-mm.
You have to put it into its y axis.
It's got to be what now?
And if they're not in its y axis, sometimes so you need to.
Yeah, there's not exactly, it's not 10 newtons that way, 10 newtons that way. Okay, draw a free body diagram for this guy right there. This guy. No, I was distracted. I want it.
I want it.
I'll take care of that, thank you. Stand up, draw a free body diagram, come on. I'll make you stand up.
No, I don't know.
You got it? Alright, so there's F. We've got 10 newtons at angle theta. Did y'all break it down? Oh, that would be 10 cosine theta. This would be 10 cosine theta. Oh my word. You okay?
Hopefully.
What's this vertical part over here? 10 sine theta. What's this over here? Same right there. So if I've got 10 sine theta, 10 sine theta going up, what must be going down to make things completely balanced? 20 sine theta. Right there. Alright, let's keep going. We're not gonna deal with that one.
Oh, man.
Alright, Newton's second law. Summation of forces in the x, summation of forces in the y. Alright, this problem is deceptively long. A golfer puts a 46-gram ball with a speed of 3 meters per second. Friction exerts a 0.02 Newton retarding force on the ball, slowing it down. Will her putt reach the hole 10 meters away?
What's a retarding force?
A retarding force? A slowing force. Okay, slows it down. Okay? Alright, let's forget everything else for the moment, but not for too long. And let's just draw a picture, okay? So whenever you have a physics thing, just sort of zone out for a minute and draw a fun little picture.
Yay.
So don't spend too much time on the golfer. I'll make the, well, it's supposed to be green, but I guess it's not. So here's the golfer. Hold.
Oh, that needs some help.
What is he doing?
Thunderman.
Well, we need a, you know what? I'm just going to draw a putter here.
What the?
What? Is that a foot?
Yeah, that's a foot, right? Oh,
Is that Pinocchio's
putter. Okay, so putter hits the ball. And as soon as it hits the ball, I need to probably make this line horizontal. The velocity,
It's
you
a
know,
shoe, sorry.
that's a shoe, yeah. My foot looks like a shoe, looks like a putter, looks like a box, looks like a whatever.
And that's
Alright, so it's gonna roll all the way over here. We don't know if it's actually going to get inside the hole. That's the it's a croquet mallet.
Oh God.
Oh.
All right. What else do we need to? Let's see. 46 grams. So the mass equals 46 grams. I don't know about you, but I don't like grams because they're not standard. So let's multiply that by something to turn it into kilograms. I want to get rid of grams. I want kilograms. What's that relationship? 1,000 to 1. So 0.046. Got it. It's going to go with a speed of 3 meters per second. Let's draw a motion diagram. Initially, when she hits it, okay, this is her play, it's going to have quite a lot of velocity. But then friction is going to slow it down. We want to know how far is it, is it going to slow it down enough that it's going to hit 0 before, at, or after the hole. Okay, what are some other things that we do when we're solving physics problems? What's that? Write down our knowns and unknowns, okay. So friction exerts a 0.02, so that's, normally use letter F, 0.02 newtons. Okay, you can find the acceleration by the force divided by mass, but I don't have the force. I have the frictional force, but I do not know exactly how hard she's hitting. I don't know that force. If I did, that'd be great. Okay, we know this is 10 meters away. If I'm going to have 10 meters, we need to have some sort of number line. Okay, so if this is meters, there's 10 right there. Well, maybe I'll make it right even with the very edge of the hole. So there's 10. It seems like that's a good place to put 0. What else do we know? Oh, I circled this, but I never wrote that down. 3 meters per second, what does that mean? Initial velocity. So Vx naught, since we're in the x direction, is 3 meters per second. That reminds me, this frictional force, what's the direction of that frictional force?
To the left.
To the left. So yeah, that would probably be negative. It's that way. Let us draw a free body diagram on this.
Yay!
Of this ball. We're going to do everything. We're going to have number line, we're going to have motion diagram, we're going to have actual diagram, we're going to have knowns, we're going to have unknowns. This is like everything. That's the great thing about dynamics problems. It's like each dynamics problem is sort of like a semester exam question.
That's so great.
I love it.
I wonder what the semester exam is like.
It's
A failing grade.
like a dynamics problem. Okay, it's just one question. Just one big question.
And you
Failing
screw it
grade.
all up.
Failing grade.
Better get it right. No, seriously though. Okay, let's talk about the free body diagram. What forces do we have acting on this? Okay, we've got normal and we've got weight. So, okay, we do have friction. Now, when are we considering this? Are we going to consider it before she hits it, after she hits it, or the moment that she hits it?
The moment.
Okay, the moment. If we consider the moment that she hits it, we have the speed. See, the friction doesn't happen until after she hits it. And when she hits, and here's the thing. Before she hits it, we don't care because nothing's going on. After she hits it, we know the friction force. If we look at it, the moment that she does hit it, we would need to know the force in which she is hitting it, and we do not know that force. So in this case, it is best for us to consider the ball immediately after she hits it. So just after it is yeah, we've got the weight force, which is going down, the normal force, which is going up, and the friction force, which we said a moment ago, is to the left. Are there any other forces acting on this ball? Right after it starts, after she hits it, no, there aren't. That's it. That's our air resistance. Yes, but we are going to neglect that unless our problem tells us otherwise. At this point, we have several different options. We can kind of start going the kinematic route and writing v squared equals and v equals and all those other things. Or we can kind of go the dynamics route and start writing Newton's second law. It's really user's choice. What do y'all want? Okay. All right. Newton's law way. Okay, great. So we can write summation of forces in the x direction. This is going to be nice and easy. Everything's positive is, or to the right is positive. Everything that's negative is, or to the left is negative. So negative f equals mass times acceleration in the x direction. If I want to, I could also write summation of forces in the y direction. Normal going up minus weight going down equals mass times acceleration in the y direction. Okay? All right. Do we know any of these? We know the mass. And we know the friction. Hey, that makes me think we could find the initial acceleration. So I'm going to solve this for acceleration. It's negative f over mass. So acceleration is, now I put negative over here to remind us that it was in the negative direction. At this point, I'm not going to put negative and another negative. It's negative 0.02 divided by 0.046. So that was newtons. Those units, kilograms, right there. Someone with a calculator, 0.02 divided by 0.046. Negative 0.43 meters per second squared. Great. Now I have the initial acceleration, or well, the acceleration is constant. So at this point, it turns into a kinematics problem. I have an initial velocity, I have an acceleration, I have a distance if I want to plug in the distance. There's also a hidden piece of information here that they didn't give you.
Final velocity of c.
Final velocity is 0. Vx, final velocity, 0 meters per second. So, just to sort of summarize it, I have acceleration, I have Vx is 0 meters per second, I have the initial velocity was 3 meters per second, and I want to know, is this object going to travel 10 meters? Is there a formula that could relate those concepts all together? What formula is that? X equals x naught plus,
No, we don't have time.
we don't have time.
Velocity
The-
squared.
Yeah, that one.
Keep going, velocity squared equals,
Velocity not squared plus your acceleration of x.
okay,
What do you want?
sounds good. Do we know V? Yep. Do we know V squared, V naught squared? Yep. Do we know acceleration? Oh yeah, we know all of that. Let's figure out the delta x. So, as always, we're going to solve this equation for delta x first. So I'm going to subtract V naught squared from both sides. So V squared minus V naught squared equals, that would just equal 2a delta x. What I can do is divide both sides by 2a. All right, let's figure out how far this ball is going to roll. So
Let's get the ball rolling.
it's already rolling. We got to figure out where it's stopping. So 0 squared minus 3 squared divided by negative 0.43
What up?
times 2.
I got it. I got it.
We have a number?
Shelby's got it first.
9 divided by, negative 9 divided by, well, that's negative and this is negative, so those will cancel out. 10.46 meters is our delta x. Great, but what does that mean?
It means that it does make it.
It does make it. Well, it reaches the hole. It at least goes.
It makes it with change to spare.
Yes, and if you've ever played putt-putt, you definitely want to hit it a little bit harder than otherwise because it just sits right here. And I've had to just hang over the edge and not even fall. And I'm like, that is physically impossible. But it does it. You want to hit a little bit harder. Have you ever hit it too hard?
Yes.
It goes like, it hits there and it pops up and, then it goes over here or whatever. So that can be annoying. But for putt, we'll reach the hole. So actually, the answer to all of this is yes. And don't you know, those video games that are golf simulations, they have to do this stuff.
I'm totally kidding.
They work it very well. There's money to be made in this industry. In the whole game industry, my video game design class we talked the other day, there's entire games built on physics.
We know.
Nice.
Yeah, funny how that works.
I was thinking more like the Angry Birds, but that's true too. All of those first time engines.
I
they
love.
spend more money on those than they do on big budget movies. Talking about the hundreds of millions of dollars. Oh, you want to see a better picture?
Show that to Joseph.
Okay. All right, let's pick this up right here. Last problem, I think, for the day. Oh, by the way, this is, in case you haven't realized it, this is another one of these situations. Kim, do I need to just holler at them to go somewhere else? Okay.
Wait, see me tripping. Oh, somebody. Get off my lawn.
Wait, so we could
Get off my
yes,
school.
yes or no.
Get off my car.
That's a waste of money.
Yes, good question. If you had just put yes or no for the answer to that question, would that have been enough work?
Yes.
Absolutely. Yes.
Whatever. So
Okay.
You only have,
Alright.
it's a 50-50 chance.
Just have
It
the answer
works.
to that. No need to show all your calculations or anything. No need to demonstrate knowledge of physics. Just answer the question. All right, seriously though, this isn't one of these situations where doing it together takes a lot longer than you doing it yourself, and also we get faster as we work. So let's see if we can do this one in less than half the time of the previous one. A car with a mass of 1,500 kilograms is being towed by a rope held at a 20-degree angle. A frictional force of 320 newtons. What is the tension in the rope if the car goes from rest to 12 meters per second in 10 seconds?
Stop.
So close.
It's the same
Yes.
thing. So the force in the x direction is 340 for the.
That was only because, the only reason why that was the case is because it was in static equilibrium.
Okay.
However, our work with the free body diagram will not go to waste because its free body diagram is the exact same. Weight going down, normal going up, friction to the left, tension, and then Tx is T cosine 20, Ty is T sine 20. All of that is the same. Alright, so if we write the summation of forces in the x direction, so that's just T cosine 20 degrees, going to the right, minus F equals mass times acceleration. What we did last time was we said, well, acceleration in the x direction is 0 because it was going at a steady speed. That is not the case this time. Now it is going from rest to 12 meters per second in 10 seconds. So I'm going to need to figure out what that acceleration is. So my initial velocity is 0. My final velocity is 12, and my time is 10. Is there a formula that can give me the acceleration?
Vx equals Vx naught plus AT.
Yeah. Yeah, you can just do that. Yes, that is correct, Matthew. That will give you the correct answer. However, also just the definition of acceleration, delta V over delta T, is going to be a lot faster, which is why you do need to have that one memorized. Okay. What the equation that you're looking at is just a variation on that formula. Okay. Change in velocity, final minus initial, 12 minus 0. Change in time, 10 seconds.
Sorry, at 12, they're gonna have the kids line out outside on the hallways.
Okay.
Why?
Well, it's
Okay,
12
2
or
minutes,
1.
2 minutes ago, they're going to line up in the hallways. So, 1 point.
It's sarcasm,
There we go.
I
Well,
can't.
that's fine. That's all right. We won't have been finished in another 2 minutes. So, or we will have been finished in 2 minutes. So 12 minus 0, so 12 divided by 10, so 1.2 meters per second squared. That's what I can put in for right here. All they're asking for is t. So I'm going to solve this entire thing for t right now and say t equals mass times acceleration in the x direction plus the frictional force, adding that to the side, and then dividing both sides by cosine 20. Aren't we loving the fact we can just substitute one thing in and we get all the answers? So tension is mass 1500 times the acceleration, we just found that out, 1.2 meters per second squared, plus the friction, 320 newtons, divided by cosine 20 degrees. Anybody have a number?
It's 0.25.
There's no way it's in the 2000 region.
Okay, bye.
Oh, maybe it is.
Yeah.
Why is it so much more?
Because.
It's accelerating.
Because it's accelerating. Absolutely right. All right.
I guess.
There you go. Make sure you read 5.3, 5.4 for Monday. 5.3, 5.4 for Monday. Today we talked about dynamics problems.
Add me on Snapchat.
Oh,
I don't